Okay, today we're going to have a look at prime numbers, just because prime numbers, mathematicians love them, and as computer scientists we kind of need to be familiar with them. If you don't know, a prime number is any number that can only be divided by itself and 1. In other words, it can't be written as a product of two other integers. So prime numbers start at 2, 3, 4, 5, 7, 11, 13, 17 and so on. It's an infinite list, so we don't really know, how long it'll go on for. It goes on forever. One thing to note is even numbers can't be prime numbers apart from 2 because they can all be divided by 2. Why are they important in computing? Well, all of the cryptography that we tend to use day to day is using public and private key cryptography, which are all based on massive prime numbers. So that's one reason they're important in computing. Also, Bitcoin and cryptocurrencies are all using prime numbers as well. However, we're going to start slow and we're going to look at how can we test if a number is actually prime using Python. So the sort of pseudocode of thinking about it would be taking a number from a user, let's call it the target number, and then run through all the numbers up to that target number and check if any of those divide into it completely, okay? And by divide it into it completely, I mean leaves no remainder. So when we're talking about remainders, we need to use the modulo or modulus operator, which is the percent sign in Python. This returns the remainder of a division operation. If it returns 0, we know that the two numbers that divide are, well, the number that is dividing is a factor of the target number. So for example, here on my screen, I've got target, if the target number is 15, for example, if we do target %6, so divide 15 by 6 and check the remainder, if you divide 15 by 6 is 2. I'm sorry, it's 3. Because 6 will go into 15 2 times and leave a remainder of 3. However, if we did target %5, so divided 15 by 5, we'd end up with no remainder because 5 goes in completely into 15. It is a factor of 15. So let's have a look at how we can do that in coding. So I've already got a line here that asks the user to enter a number. I'm also taking whatever they've input and converting it into an integer using the int function. So as I discussed before, we're going to create a loop using the for keyword, say for I in range. Now I could just do range number, so we'll just go up to the number that the user has just entered. However, it's going to not work because, first of all, it starts from 0 and we don't want to be dividing anything by 0. But also then if I change it to 1, then everything divides by 1. So I'm actually going to start from 2, okay? So that's important. We need to start from 2 and go up to, but not including the number. And then inside the loop, we're going to test whether or not I, which is our variable, will divide into the number that the user's entered. So we're going to use our modulus function, which is I, it's not a function, it's an operator, I % and then number. So that will return, I'm sorry, I got it the wrong way around. Sorry, number % I. So that will return nothing or 0 if it is a factor. So that, or if it's equal to 0, we know that I is a factor of the target number, okay? So let's just see what happens. If I just say print not a prime, yes, I know this isn't complete and I know it's not perfect, but this should be enough just to do some quick checking. So if I run it, and there we go, enter a number to check that it's prime. So I'm going to type in something that's definitely not a prime, 222. And I get it saying not a prime, so it's kind of working. The slight problem is if I enter a number that I know is a prime, for example 17, it does nothing because we haven't got anything that actually checks whether it's a not a prime. So it's kind of working, but it's not there yet. What I might do is just show you something quite cool before I change this. If I just stick that I variable onto the end, we can explain why it was coming up with 4 not a primes. Okay, so if I run that now, and I'll type the same number in, 222, which we know is not a prime, can you see here that it's actually printing out the factors of 222? So 2, 3, 6, 37, 74 and 111. So that's kind of a nice trick there to work out what the factors of a particular number are. But that's not what we're doing here, so I am going to get rid of that. So what I want really is a flag variable. I call them flag variables. These are little variables that are either true or false. So up at the top here, I'm going to just assume that the number that they have typed in is a prime. So I'm just creating a variable called prime and setting it to true. However, if inside my if statement, we get to this point where number %i is equal to 0, we know it's not a prime. So I'm going to switch that flag variable back down to false again. Okay, so far so good, but we want a message at the end, don't we? So we can write a little if statement, say if prime is equal to true, then we can say print, let's be a bit cleverer, let's say number is, oops, I'm just sticking with commas here, number is a prime number. Okay, again, I can probably hear loads of you shouting, this isn't the most efficient way of doing it, but let's just stick with this for now, okay, is not a prime number. Right, so let's try that again, run it with the same two numbers we ran with it before to make sure our testing is accurate. So 222, it says 222 is not a prime number, and if I run it again, and type 17 in again, it says it is a prime number. So far, so good. Let's try it with a big prime number and see how it performs. Now, I don't know many big prime numbers. I know one, but let's just try it with a big number. What I really want to start to look at is how we can make this a bit more efficient. So I'm just going to type in a big number, 1, 2, 3, 4, 5, 7. I'm pretty sure that's a prime number. So, okay, that was quite quick. Let's try another one again. All right, so 1, 2, 3, 4, 5, 7. 1, 2, 3, 4, 5, 7. That's a pretty big number, yeah? Now we can expect to wait for a long time with this. In fact, longer than I want to wait. So let's now have a look at how we can time these functions and then look at how we can potentially improve these functions. We're going to look at how we can time our programs. Okay, this will help us to show us how efficient our programs are, and anything that we change, we can see if it speeds it up. By the way, it still hasn't finished working out if that's a prime number yet, so I'm going to just cancel that because that was taking too long. Okay, so in order to time it, there are lots of different ways of timing it, but I am going to do the one that seems to work the nicest for me. I'm going to use a function of the time library called time. Okay, if I just do a variable, so up at the top I'm going to import time, and I'm going to create a start time variable here at the beginning. So I'll wait until they've inputted a number because users take a long time to write things sometimes. So it's time.time, okay, and then when it's finished here, we'll do end_time, and I will set that to time.time. Then I am going to, at the end, I'll print out, oops, sorry, print seconds. I'm hoping it's in seconds. And then I am going to do a string of end time minus start time. Have I spelled that all right? Yeah. And finish off the brackets. Let's see if that works. So let's say, okay, let's do it with our famous numbers. It took 0 seconds to work that one out. And if I do run it again with a slightly larger Let's do 1, 2, 3, 4, 5, 7. There we go. You can start to see the seconds creeping up. Let's run it again with a slightly bigger number. 1, 2, 3, 4, 5, 6, 7, 8. We know that's going to be not prime. It's starting to take a little bit longer. Now, how is it, there you go, 7 seconds. How is it that us lowly humans could work out that's not a prime number much quicker than a computer could? It's the way that my program is working, okay? It works, but it's not the most efficient because already, you know, with a slightly larger number, it's already taking sizable amount of seconds. I suspect that if I ran that again and did 1, 2, 3, 4, 5, 6, 7, 8, 9, it could still take quite a long time. So while that's chugging away in the background, let's have a look at the code. Now there's a few things we could do. There's one that will make it a whole lot easier, but let's have a look at this range here. Do we really need to go all the way up to the top number? Well, the answer is no. I can go up to, so if I just put that in there, that's basically doing an integer division by 2. It is basically taking me up to halfway up the number. If it hasn't found the factor then we know that it's a prime number. Okay, so that should already reduce the search space by at least half. So we should hopefully get a much quicker result. So I'm going to actually cancel. This one's taking far too long. It still hasn't returned a number, so I'm going to Control-C out of that. Let's go back to this one where it was 1, 2, 3, 4, 5, 6, 7, 8, which took 7 seconds. Now that I've changed it, I'm hoping if I do 1, 2, 3, 4, 5, 6, 7, 8, it should not be 7 seconds, but 4 seconds? There we go, 3.5, there we go. So it has actually sliced it in half. So already we're making our code a bit more efficient. There is a theory as well that we can do the square root of a number, which is slightly less than half. Well, it will be less than half. So that would make it even faster. So that's one way of making it more efficient. But if I quickly also import the math library, and instead of doing number divided by 2, I do math.sqrt, which is the square root of number plus 1. Oops, plus 1. Okay, let's try that. So let's do the same number. We're checking 1, 2, 3, 4, 5, 6, 7, 8. Oop, what have I done? 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 I think I need to do... I might be completely wrong with that. Is it math apps? How do I, oh, maybe it's math.brand. Oh, tell you what, I know, I'll just do int, sorry. If I just, yeah, let's try that. Why not? Because it was a float, that was why it complained about that. I should always check my code before I run it, shouldn't I? There we go, wow. Okay, so I've added the square root effect. The square root effect? The square root function in there. So basically this just shaves off a few more numbers that we need to check. There's also the theory that you don't need to necessarily check every single number because you could do it, start from 3 and then go up in, I've seen this one, let's try this again. So if I go up in 2s, it only then checks odd numbers, it doesn't bother with the even numbers, so this might make it even faster. So if I save that and we'll still try our 1, 2, 3, 4, 5, 6, 7, 8 number here. There we go, it's making it even faster. Okay, this is what real programmers do. They keep shaving seconds off, which could make the difference between a slow, unusable website or game to something that's a bit more responsive. So any of these marginal gains will really help. I've got a bigger number that I wanted to try, which I'm going to try and remember, which is a prime number. So we've been trying big numbers that are not prime. Let's try a big number that is prime. So if I run this now and see, try and remember it, 1, 5, 5, no, 1, 3, 3, 5, 5, 5, 7, 7, 7, 7. Okay. It is a prime number. That didn't take too long, actually. There are some really big prime numbers out there, so that one's not too bad. Now, there is one glaring thing that we can do to make our program not need to go through all of those numbers. Okay, as soon as it's found a factor, it should stop. And this is the one that, even without worrying about all of these ranges and changing the search space that we're looking through, what I can do to significantly improve the performance of this code is to simply put a break in there. As soon as we found a prime number, as soon as we found a factor and we know it's not a prime, just break out of the loop. What is the point of looping through every other number? As soon as we know there's a factor in there somewhere, just kill it, okay? So if I run that again, and with our big old number here, not the one that is prime, but the one that isn't prime, so 1, 2, 3, 4, 5, 6, 7, 8, which previously was taking, well, it wasn't taking very much time at all. There we go, it's now down to 0, because as soon as it realises you can divide it by 2, we're in the money, okay? It won't necessarily make it faster if it is a prime number, but it does mean that we can stop looking once we've found at least one factor. Okay, so hopefully this has been useful. There's a nice bit of code there. I'll share the link to the code in the description below, and hopefully this will help you understand prime numbers and how we can use them in Python a little bit more.